We now start chapter 2 module 7 and we will learn some basic constructions like sum of subspaces, direct sums, the internal and the external ones, quotients, and we will also learn some very important theorems on quotient spaces called the isomorphism theorems. Let us start. Let F denote a field and V a vector space over F. Let W1 and W2 be subspaces of the vector space V. Then it is an easy verification that the intersection of subspaces, that is W1 intersection W2, is a subspace of V. But the same is not true for the union. For example, if we take V to be the real plane, that is R2, and W1 is equal to set of all ordered pairs of the form x comma 0, where x is running through the set of real numbers, and W2 is the set of all ordered pairs of the form 0 comma x, where x is running through the set of real numbers. That means W1 is nothing but the x axis and W2 is the y axis. Then the union W, that is W1 union W2, is not a subspace. Why? Because if we take the element 1 comma 0 from W1 and the element 0 comma 1 from W2, then their sum, which is nothing but the pointwise addition, is 1 comma 1, but that is clearly not in W. Now we prove a very interesting fact which says that if F is an infinite field and V is a finite dimensional vector space over the field F, then V cannot be written as a finite union of proper subspaces of V. Here infinite field plays a very important role, because this statement is not true if F is not an infinite field. Let us prove this statement. Suppose that W1, W2 and so on Wk are subspaces of V such that V is the union of W1 and so on up to Wk. We can assume that W1 is not contained in the union of the other Wj's. That means W1 is not contained in union Wj j not equal to 1. And therefore, we can choose a vector W in W1 which is not in the union of the other Wj's. And it is understood that these W1 and so on up to Wk are proper subspaces. Therefore, we can choose a vector V which is in the vector space V but not in the subspace W1. Let us consider this set T, which is the collection of all linear combinations of the form Cw plus V, where C is running through the field F. We show that each Wi contains at most one vector from T. At most one vector means either Wi intersection T is empty or a singleton set. This will surely contradict the assumption that V is equal to W1 union and so on union Wk, because T is an infinite set. Why is that so? Because you can see that the scalar C is running through the field F and the field is an infinite field. And not only that, for distinct values of C, we get distinct vectors in T, and therefore T is infinite, and then T intersection Wi must be infinite for at least one I. But if we can show that T intersection Wi has at most one vector, then we have a contradiction. So let CW plus V belong to W1. We know that W belongs to W1, therefore, it follows that the vector V also belongs to W1, but that is not possible because of the choice we have made on V, that V is in the vector space V but not in W1. Therefore, W1 intersection T is an empty set. Now, suppose that for scalar C1 not equal to C2, the vectors C1W plus V and C2W plus V of T belong to Wi for some I not equal to 1. Subtract these two vectors and then we get C1 minus C2 times W, and that must belong to Wi because Wi is a subspace, and therefore, C1 minus C2 being non-zero element in the field, we get W belongs to Wi for some I not equal to 1, which again contradicts our assumption on W because we have chosen W which is in W1 but not in the union of Wj for j not equal to 1. That means W belongs to the subspace W1 and avoids all other subspaces from W2 to Wk. This completes the proof. Definition: let W1 and W2 be subspaces of V. The sum W1 plus W2 is defined as the collection of vectors of the form V1 plus V2 such that the vector V1 is from the subspace W1 and the vector V2 is from the subspace W2. In general, if Wi, I belonging to lambda, is a collection of subspaces of V, then the sum is defined as summation Wi, I belonging to lambda, is the collection of all vectors which are finite sum of the form V1 plus V2 and so on up to Vk, such that the vectors Vi are in union of Wi, I belonging to lambda. So, first we defined sum of two subspaces and then we extended that definition to sum of a family of subspaces, and you can see that the set lambda is an index set, and this index set could be finite, could be infinite, could be countable, uncountable, anything. Now, again it is an easy verification that the summation Wi, I belonging to lambda, is a subspace and it is the smallest subspace containing all the subspaces Wi. Let us prove this theorem, which talks about the dimension of the sum of subspaces. So, let V be a finite dimensional vector space over F. Let W1, W2 be subspaces of V, then dimension of the subspace W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. How to prove this? Let us start with a basis for the subspace W1 intersection W2 and call it U1, U2 and so on up to Uk. Remember that V is finite dimensional, therefore, every subspace is finite dimensional. We have already seen this as a theorem in one of the previous modules, and now we also know that we can extend this basis of W1 intersection W2 to a basis for W1, and we name it U1, U2, Uk and so on, V1, V2, Vm, and also to a basis of W2 and name it as U1, U2, Uk and so on, W1, W2, Wn. If we can prove that this set of vectors U1 and so on Uk, V1 and so on Vm, W1 and so on Wn is a basis for W1 plus W2, then we are done, because dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2 is precisely m plus k plus n plus k minus k, and that is the same as m plus n plus k. That is precisely the desired value. So, let V be a vector which is of the form V1 plus V2. That means it is in the subspace W1 plus W2, because V1 is in W1 and V2 is in W2. Then V1 belongs to the span of U1 and so on UK, V1 and so on Vn, and V2 belongs to the span of U1 and so on UK, W1 and so on Wn. Therefore, it follows that V, that is equal to V1 plus V2, actually belongs to the span of U1 and so on UK, V1 and so on Vm, W1 and so on Wn. That is easy to see if we write the linear combinations. We now show the linear independence of this set U1 and so on UK, V1 and so on Vm, W1 and so on Wn. Let us start with a linear combination of these vectors, equate that to the 0 vector. So, you can see Ai, Bj, Cls are scalars, and we have this linear combination which is the same as the 0 vector. Then we just push that summation Cl Wl L equal to 1 to n to the other side of the equality sign. Then the vector on the right hand side of the expression belongs to W2 and the vector on the left hand side of the expression belongs to W1. Therefore, this summation L equal to 1 to n Cl Wl actually belongs to the intersection W1 intersection W2. Therefore, we can write summation Cl Wl L equal to 1 to n is equal to summation di ui I equal to 1 to k, because we know that the set U1 and so on UK is a basis for W1 intersection W2. Now, we apply linear independence of these vectors U1 and so on UK, W1 and so on Wn, and we get Cl is 0 for all L from 1 to n. Therefore, that big expression reduces to this summation I equal to 1 to k Ai ui plus summation j equal to 1 to m bj vj is equal to the 0 vector, and now we apply linear independence of the set of vectors U1 and so on UK, V1 and so on Vm, and obtain Ai is 0 for all I from 1 to k and Bj is 0 for all j from 1 to m. Therefore, we have proved linear independence and we are done. Now, we define the direct sums. First, let us define what is called the external direct sum. So, we start with n vector spaces V1, V2, Vn over a field F. The external direct sum is denoted by that symbol V1 box plus V2 box plus and so on box plus Vn, and that is a vector space where the underlying set is nothing but the Cartesian product of V1, V2 and so on up to Vn. That is the collection of all these n tuples V1, V2 and so on up to Vn, where Vi belongs to the vector space capital Vi, and the vector space structure is with respect to the pointwise addition and scalar multiplication defined in the usual way. That is, the vector V1, V2, Vn plus the vector W1, W2, Wn is the pointwise addition V1 plus W1 and so on Vn plus Wn, and the scalar multiplication is given by C dot V1, V2, Vn is equal to C dot V1 and so on C dot Vn. That is true for every n tuple V1, V2, Vn and W1, W2, Wn in V and C in F. And now we define an internal direct sum. A vector space V over F is called an internal direct sum of the subspaces W1, W2 and so on Wn of V, denoted by V is equal to W1 O plus W2 O plus and so on Wn. You see that we have used a different symbol here for internal direct sum, and this is called an internal direct sum if the following properties are satisfied. That is, V is equal to the sum of these subspaces W1 plus and so on Wn, and Wi intersection summation Wj j not equal to I is the trivial vector. In other words, every element V in V can be expressed as V is equal to V1 plus V2 and so on up to Vn for unique choice of vectors Vi coming from Wi. Example, the vector space f raised to n, which is the Cartesian product of f n times, is the external direct sum of the vector spaces f n copies. On the other hand, it is an internal direct sum of the subspaces Wi given by that Cartesian product which you see over there, where only the ith spot has f and every other spot has the trivial subspace, namely singleton, the 0 vector. Another example, the vector space M and F, that is a collection of all n cross n matrices over the field F, can be seen as an internal direct sum of these two subspaces SNF and ANF, where SNF denotes the subspace of symmetric matrices and ANF denotes the subspace of skew symmetric matrices. This is an interesting observation, and this follows from the fact that we can write A as A plus A transpose over 2 plus A minus A transpose over 2, and it is indeed an internal direct sum. That means this expression is unique. We now define a very important construction of quotients, quotient of a vector space by a subspace. We will define it by defining an equivalence relation with the help of a subspace, and we will see that quotient also has a natural vector space structure coming from the vector space structure of V. Let us first learn the definition, and then we will learn some theorems which will talk about subspaces of quotient spaces and also about the dimension of quotient spaces. Definition: let W be a subspace of a vector space V over F. A coset of W in V is a set of the form V plus W, that is the collection of all vectors of the form V plus W, where the vector W is in the subspace W for some vector V in the vector space V. Example, let V be the vector space R2, W the x-axis, and V is the vector 1, 1. Then the coset V plus W is the set of ordered pairs of the form x plus 1, 1, where x is running through the set of real numbers. And you can see that this is the line passing through 1, 1 and parallel to the x-axis or the subspace W. In fact, if W is a line passing through 0, 0 in R2, then the cosets of W are lines parallel to W. Proposition: let W be a subspace of a vector space V over F. Let V1 plus W and V2 plus W be two cosets of W in V, then exactly one of the following holds: V1 plus W intersection V2 plus W is the empty set, or V1 plus W is equal to V2 plus W. Moreover, V1 plus W is equal to V2 plus W if and only if V1 minus V2 belongs to the subspace W. It's a very simple observation. How to go about it is that if we assume that one is not true, that means if they have an element in common, then we start with that element and then we prove 2. Let us now define an equivalence relation on V in the following way. We know that W is a subspace of the vector space V over F. Now, given vectors V1, V2, we define V1 is related to V2 or V1 tilde V2 if and only if V1 minus V2 belongs to the subspace W. In the language of cosets, V1 tilde V2 if and only if they define the same cosets with respect to W, that is V1 plus W is equal to V2 plus W. It is an easy verification that tilde is an equivalence relation on V, and given a vector V, the coset V plus W is the equivalence class of the vector V, and we often use V bar to denote the equivalence class V plus W. Let us take the collection of all these equivalence classes and we denote that set by the symbol V slash W or V by W, and that is called the quotient set. The elements of the quotient set are therefore equivalence classes or cosets. We can define addition and scalar multiplication on V by W in the following fashion. For vectors V1, V2 in V and scalar C, we define V1 bar plus V2 bar is V1 plus V2 bar, and C times V1 bar is CV1 bar. One has to be careful while defining operations with equivalence classes and make sure that the well definedness is satisfied. For example, if V is the vector space R2 and W is the x axis, then you can see that the equivalence class of 1 comma 1 and the equivalence class of 2 comma 1, they are the same. Therefore, one has to check that the definition of the operation that we define does not depend on the representative of the equivalence class or coset. The following theorem says that if W is a subspace of the vector space V over F, then these operations defined on V by W are indeed well defined. How to prove that? We first assume that V1 bar is the same as V1 dash bar and V2 bar is equal to V2 dash bar. That means the same equivalence class has two representatives, and then use the definition of equivalence relation to prove that V1 plus V2 bar is the same as V1 dash plus V2 dash bar, and C dot V1 bar is the same as C dot V1 dash bar. Theorem: let V be a finite dimensional vector space over a field F and W a subspace of V. V mod W or V by W is a vector space with respect to the addition and the scalar multiplication defined above. The additive identity of V quotient W is the element, the 0 vector of V bar, that means the equivalence class of the 0 vector of V. And part 2 says that dimension of V quotient W is equal to dimension of V minus dimension of W. One is a routine verification. Now for part 2, we follow the following steps. Let W1, W2 and so on Wm be a basis for W. We extend this to a basis W1 etc. up to Wm, comma V1 etc. up to Vn for V. Then it is easy to see that the vectors V1 bar, V2 bar and so on Vn bar span this quotient space V quotient W. Moreover, this set of vectors V1 bar and so on up to Vn bar is linearly independent over F. Hence, the set containing V1 bar and so on Vn bar is a basis for the quotient space V quotient W, and dimension of V quotient W is n, that is n plus m minus m, that is dimension of V minus dimension of W. Now the so called correspondence theorem, which talks about the subspaces of V quotient W. So let W be a subspace of a vector space V over F. Let us look at this set S, which is the collection of all those subspaces T such that W is contained in T and T is contained in V. Now the map eta defined from S to V quotient W given by eta of T is equal to T quotient W is an order preserving 1-1 correspondence. This therefore shows that the subspaces of V quotient W would be of the form T quotient W, where T are subspaces of V which contain W. Now, the so called first isomorphism theorem, which says that if V and V dash are finite dimensional vector spaces over a field F, and F from V to V dash is a linear transformation over F, then there is a well defined 1-1 linear transformation F dash from V quotient kernel of F to V dash, and the definition of F dash is F dash of V bar is F V bar. Moreover, F dash is an isomorphism if the linear transformation F is onto. The second isomorphism theorem says that if V is a finite dimensional vector space over a field F and W1, W2 are subspaces of V, then these two quotient spaces are isomorphic. One is W1 plus W2 quotient W2, and the other one is W1 quotient W1 intersection W2. And the third isomorphism theorem says that if V is a finite dimensional vector space over F and W1 contained in W2 are subspaces of V, then V quotient W1 quotient W2 quotient W1 is isomorphic to V quotient W2. See that on the left hand side, W2 quotient W1 is indeed a subspace of V quotient W1, because we have W1 is contained in W2, and by the correspondence theorem W2 quotient W1 is a subspace of the quotient space V quotient W1. In this module, we have learned two very important constructions. One is the construction of sum or direct sum, to be precise. We talked about internal direct sum and external direct sum. We call it internal direct sum when we are taking sum internally, that means we are taking sum of subspaces of a given vector space. And when we call a vector space is an external direct sum of vector spaces, we mean that we are taking the sum externally. That means we have finitely many vector spaces and we are creating a new structure out of them through pointwise addition and scalar multiplication, and that is what we call an external direct sum. We have seen examples, and then we learned the concept of quotients, which is another very important construction for various reasons. And we have learnt quotient for vector spaces in general, but when we want to talk about the dimension, then we have restricted ourselves to finite dimensional vector spaces only.